Testing. All right. Hey guys, what's going on, Danny? Today we're going to be going over arrays and linked lists. This is going to be the first of many videos talking about data structure and algorithms. I want to prepare you guys for like LeetCode interviews and stuff, so I want to talk about things from the ground up first. So that's why I'm starting with arrays and linked lists. It's pretty foundational, but I think it's going to help out with a lot of the later videos that I plan on making. So yeah, let's get into it. Okay, cool. So I made this like little thing here. Basically, one thing in this video is I'm going to talk about like what an array is and how it works, and then I'm going to solve a LeetCode problem with it. And then I'm talk about linked lists and what those are, and then I'm going to solve a problem with those two. First, like, what is an array? So, an array is just a continuous block of memory. So, if you're familiar with like an array in regular coding, right? Like, it's just a collection of elements, right? But more importantly than that, those elements are stored in continuous blocks of memory, meaning that they're all next to each other in order, perfectly together. There's no separator, there's no space. They're all in the exact same spot, like in your computer, basically. And another important thing is, I guess, it stores the same element, and that's what allows you to maintain this structure, because each individual, like, I guess, indice inside that array will be the exact same size, and that'll allow you to index properly, which we'll talk about in just a second. So more importantly, as I said before, all elements in the array are stored sequentially. You can see all the references are incremented by 4. This is base 16, so every 4 just increments by 1 indice. And this is the formula for it right here. And then, for example, like why indexing is O1 is because of this formula right here. You can just instantly access any index because you know exactly where it is in memory as long as you know where the base address is. And that's why you store the reference of the array. And then time complexity, this isn't too crazy. Accessing the index is normal. Searching and unsorted, in the worst case scenario, you'd have to check every single element in order to find the element you're looking for. And then inserting an index, is all that because if I were to insert like right in between here, there's actually no space in memory in between here. So what I have to do is I actually have to shift each individual element down 1. And this is different in other types of arrays, like, but for the arrays that we're talking about today, that you can't shift down. Well, I guess linked list more specifically, it's a bit different, but yeah, in order to insert an element here, like in between these two, you'd have to get rid of the 30 and bump the 30 down, bump the 40 down, and then extend the length of your list and add 50. Which is a very expensive operation, which is why it's O of n. Pending at the end is just O of 1. You just add size. And amortize just means that every now and then, basically when you declare an array, there will be space allocated for it dynamically or already. But as you add more and more elements to it, it'll dynamically reallocate space. So basically, this array, only these reference values are stored. Basically, as you add another element, what they might do is they might claim more space in memory for that array. And that's why it's O of 1. And then deleting, if you were to delete or like remove something, just like inserting, you'd have to shift everything back 1. So that doesn't work. I'm not going to go over the syntax too much because it's kind of clear. I just want to actually get into solving this problem. Yeah, let's just solve it. Cool. So this is like my first time seeing it too, so I'm going to be solving it live. I'll talk about, I guess, my problem solving process and stuff. I'll use Java, or I'll use Python for this one. I'll use Java for the next one. You have an integer array nums sorted in non-decreasing order. So I have an integer array. Non-decreasing means that at every element it can do something like this, but eventually it will increase again. Remove the duplicates in place such that each unique element once. Elements num to be k. Yeah, so it looks like if I had an array like this, I'd want to remove the duplicate elements like this and this. Except I'm removing in place, which means we can't actually do that because that would leave this right here, right? If we were to remove that 1. So instead, as I talked about before, if I were to just remove from an array, that would be an O of n operation. So if in the worst case scenario, I could have n duplicates in the list. And if I had to remove all n from the array, that's O of n squared, which isn't great complexity. I bet there's a way to get O of n some way else. And one reason I know it might be O of n is because I've given a 1D array and not many other variables. Typically, if you're given a 1D array, it'll be O of n in some form. Unless you're comparing elements, then it might be O of n squared. Or if you're making subarrays or subsequences. But if you're pretty much looking at each number in isolation, you'll be fine. But this is also going to rely on a set. So I think the first thing I want to do is I want to make a scene equals a set. And then I'll add and remove things from it. Or actually, I'm gonna do this in Java because I like sets in Java better. So, oh, I haven't saw in Java in a while. So hash set, we're gonna declare a hash set of type integer, and we're gonna call it my set, and we're gonna store into that variable a hash set, a new hash set specifically. So we're creating a new object of type hash set, and we're storing it into a variable, an integer variable called my set. And in later Java versions, you don't have to put this here, but just for clarity, just like the AP exams, I'll put integer there. So now we want to go through every element in nums and remove the duplicates. So the first thing I'm thinking is we need to go left to right through it. So I'll make a for loop. So as I'm going through, if my set that contains key I, so if I already have this set contained, then it's a duplicate. So I gotta do something about it. Otherwise, if I haven't seen this set before, let's add it to the list because that means it's a unique element. Alright. And inserting into a set is O of 1. So we're storing all the elements in there because this will allow us to easily check for duplicates. Sets are like the thing you almost always do when there's duplicates because it the way it works is hashing and all this other stuff, which will be for another video, but that's not really important today. Instead, we're talking about like well, the first common. What do we return at the end? The first element in sorted order. Okay, so basically what I'm thinking is we need a two-pointer approach where as we have this array, as we go through, if we see a duplicate, we want the other one to keep going and fetch the next thing and store it there. So I will keep incrementing through, but an IDX is going to be 0, and that's going to start here. So if we've seen this, if my set already has the key, that means it's a duplicate, which means index does not get incremented. If it's a new element, index will get incremented. Because that means that we're ready to store the next element somewhere in the thing. Okay, so if we've already seen this element before, then I needs to progress, but we want to replace it with the next time we see a new element. So this is the time when we see a new element, and we want to set nums at the index. So whenever we see a new element at our placeholder, which is our left pointer, this is our slow pointer. So as we're going through this array, we're gonna have a pointer that's lazy. So whenever we see an element that's a duplicate, it'll stay here on this 1 until we find a new element, right? See, it only gets increment when there's a new element. So we start here, 1, that's a new element. We add it to the set, and at that index, that number can equal, which is right here. We can set this number equal to the same number. Now, index will increment, so now the slow pointer's here and the fast pointer's here. My set already contains this key, which means we want I to increment past this and then leave index sitting in the dust. So we have our fast pointer here and our slow pointer here. Our IDX is waiting for a new element to fill nums always. So we're always going to fill index with the new element. And index I is the element that we're seeing if we want to put it there. If it's new, we put it there. If not, we skip. Then my set that contains key, we can just increment index. But now I'm seeing, I think we can flip this code and then test it. And the reason for that is it'll be way clearer. Do this. So there's a duplicate, increment index. I'm not sure if this is correct though. So if we see a duplicate element like 1, that doesn't necessarily. We only do it if we see a new element. Which doesn't contain the key. It's a new element. So if we see a new element like 2, otherwise it's a duplicate, which means the I will continue through. The fast pointer will keep going. until we haven't seen it before. Once we haven't seen 2, this if statement will run. We'll add 2 to the set, and then add our slow index. We'll set it equal to nums at I, and then we'll increment our slow index. And at the end, we can return nums. So this might be the answer. What I'm going to do is I just ran through the response out loud in my head, and now I'm going to run the code and see if it compiles. Oh, I is less than nums. So my set that contains key I is not working. Maybe I have that syntax wrong. Maybe it's... I thought it was contains key. Maybe it's because of the not in front of my set messing things up. So we'll do this. No, we'll try just contains. Then return the number of unique elements. The number of unique elements will actually be equal to the index, probably -1, but I'm going to test index. So if that test case, we return the output. So we didn't actually replace it. So when we saw my set does not contain I, we added 2 to the set, and the number at the index index. Let's try index -1. What can we going around here? Okay, so I'll walk through it again. So we start with a pointer at 0. Boop, 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 boop. They just make it easier for me to say things. So we start with index x here, and we also start with I here. Then I increment. If my set does not contain I, it doesn't, we increment. So my set, we add 1 to the set. Number at the index, the number at 1 is going to equal 1. And we increment the index by 1. So now x is here, I is here, and these before elements are scrapped. And now my set does not contain it, so instead I should just increment. So now I is here. Okay, I increments again. Now we have I is here for 3. So my set does not contain it. That statement evaluates to true now. So now we're going to add 3 to the set. Number at that index is going to equal number at I. So number at 1 will equal 3. Equals nums at I. Then we increment index plus plus. So at the end, it looks like maybe we have an off by 1 error. Huh. Let's read it again. I'm going to do because return the number of unique elements k. We can also just return my set.size. This will tell me all of the unique elements that can do within our set. That's probably the better way to do it. So output is 1, 1, 2 when we start with an array. Oh, someone just disconnected. What? We good, bro. I'm definitely not ending this video. I'm sorry, guys. If I think it's this contains thing. I don't think this is how the function works. I think this contains key. So now I'm going to look at documentation. Hash set documentation show. I'm not going to use AI. I'm not going to cheat. Explanation. That contains key was a thing. I guess not. Constant time performance for contains. So Maybe I'm prematurely incrementing. Maybe I'm incrementing too late. If it's a duplicate, it should just sit at the next. Like anytime we see a new one, it should just go up +1. Remove the duplicates in place such that each unique element only appears once. Dot out dot print line. Set does not contain I. And we're also going to print that index. I'm chopped, bro. It's not contains key. It's so weird. Set does not contain one. Oh my god, I'm checking. one little bug. Unlucky. It should all compile now. Oh, wait, no. Yeah. Wait. What? Not my set contains nums at I? Now I right. Did it run right? Remake the testing block. The set does not contain 0. It's still. And then it increments anyway because so the set should not contain 1 initially. And until link is 3, set does not contain 1. So if that runs, oh, it's nuns.I again here too. Oh god. Little things. Bro, I'm chopped. Should work. All right, so this problem. Oh, back complexity. There's probably a milliseconds. Yeah, so right there, that just took time. So that's a lot of LeetCode is, I guess. I don't know. I am gonna post the whole problem solving process. That happens sometimes. Okay. Okay. Now let's talk about linked lists. So what's a linked list? Linked list is just a pointer of nodes. So basically, if you're familiar with a reference from like 2D arrays in Java, that's a big stressor, right? Like you can't set a 2D array equal to another 2D array. That'll create a reference copy instead of a memory copy in Java, which is a kind of a notable occurrence because if you guys have taken CSA, you've probably seen that before. But for a linked list, these nodes aren't contiguous sequences of memory. They're not all next to each other, so there's no index math. So to access different things, you actually need to pass through it. But on the offhand, you're not actually storing all n elements inside of your reference, right? Like when you're restoring your array, you're taking up that much space exactly. But with linked list, you're not taking that much space, and your reference is way smaller in memory. Like no, I guess they both have memory addresses. I don't know, but each one lives in a memory address, and they just contain a reference to the next one, and also a value for themselves. So a node class might look like this, where it has like, I guess I define it as like a recursive relationship, a recursive constructor where it will by default have a null next, but you could set to something, and then Python's right here. Oh, excuse me. So what reference is really so reference is just a memory address. It just tells you where it is. And then as far as traversal goes for linked list, it's O of n. You have to like actually pass through all the different parts of it. Think about like if you're traveling to the beach, you have to go through all these different traffic lights to get there. You can't just really skip to the end. You have to go to every single one. Weird analogy, but yeah. And then if you were to like insert at the head, it's O of 1. Basically, all you would need to do is, I guess right here, you would make a new node at the head, or if you had like your linked list, like one thing, you could just put another node in front of it, and then point that node to your previous list, and then set the front of your list to the new node that you made. And that's exactly what this logic is describing here. That's very common, something you'll see. And also, I'm going through these things kind of fast. I'd recommend slowing down and, I guess, rewatching things if you don't get it. I don't know. These are pretty fundamental concepts that will you'll be confused in the later videos if you don't get it now. Then inserting out a tail is O of n because you don't actually have access to the tail right away. Sometimes you will in certain data structures, but oftentimes you have to iterate through the whole thing. So you have to keep iterating through it until you get to the end, and then you'll have to insert it there. It's more the searching that takes the time than the insertion at the end. Inserting at the end is easy. It's just right here. But to actually get to current to be the correct value that you want, you need to search through the whole linked list to reach the end. Then deleting nodes is really easy. That's also O of 1. You can just like pull a traffic light out of the list and just kind of drive around it, which is what happens here. Let's see. Okay. Like right here, my next one equals my next one. So if I'm 1, think about 1, 2, 3. After 1 is 2. So 1.next equals 2. 2.next equals 3. If you do 1 equals current.next, that's going to equal 1 to 3. That's going to skip over the 2, and that's exactly what this code does. Then operations, the kind of described above. Accessing is O of n, because you have to check every single element you have to go through. Worst case scenario, you have to go through every single element. Inserting is easy. Inserting at the end is difficult. And as I said before, tail pointer. Sometimes you'll have a pointer at the very end of it that makes it really easy to insert and just makes it constant time. Searching, same thing as accessing. To actually find if an element exists and search for it, you have to check every single possible element, and you don't have access to them all at all. This is the same in the right, so this is nothing crazy. And then deleting it, O of 1, that's easy to just take it out. Memory scattered, yeah, all that stuff. Yeah, okay, reverse a linked list, bro. I'm chopped. I can't reverse a linked list. This is like a stereotypical type problem. Like, this is a very good one to get started with. I've never solved it in Python before. Let's do Python. So the way these usually start is you'll have your initial reference, which is head, but then you'll also want to make a new node. So maybe we'll make list node cur. I don't think I'm finding that right. I'm just using Java. I don't care. Okay, list node cur equals new list node, and what arguments we're going to pass into it. We're not going to pass any arguments. Instead, we're just going to point it straight ahead. Now we have list node cur equals head. And the reason we need that is if we're returning the reverse list, well, I guess let's start to walk through it. So I know that accessing through an array is a linked list is O of n. If I had to go through every single element, so I think this algorithm is going to be O of n because I need to go through every single one and change their next pointer to go backwards. So how am I going to do that? So my current's equal to the head. I'm looking at 1. Well, 1 right away doesn't have any value, so we can actually just go to the next right away. But let's check our conditions. Number of nodes, we could have 0 to 5,000 nodes. So if head equals null or head.next equals null, this means that it's already reversed because it's an empty list, and we can just return head. Then the next thing, and also a note on this, if we were to run head.next before this command, before checking if head is null, if head is null, then there's no next field to check, so you would get an error right away. But the way Boolean statements work in Java is that this statement is evaluated first, and so once it sees this OR, it knows that it can just stop right away, and it will exit the program. So it'll exit the if statement right away, so it doesn't actually throw an error for this one if the head is null. So if not, we release 2 elements. So let's know cur equals head.next. So now we have our current element, which is the second one, and we have head at the first. So let's also make a last element for the last one we were at. Let's know previous equals head. All right. And then let's just go until current is null. So while cur does not equal null. So we have this current node here. We want to set cur.next equal to the previous node. But this causes an issue. What is it? Think about it for a second. Okay. The current.next, if we were to change the reference for the current.next, we would lose the next node. We would lose the entire list. So instead, we need to have temp, or list node temp equals cur.next. So now it's saved. Equals previous. So now 2 is pointing at 1, and we have 3 saved. Now we can set our current node to temp, and they continue. So now we have 3, and we need to point it at 2. We can do that very easily. And at the very end, we should just be able to return head. But not return head. We should be able to return not cur, prev. So after we go through every single element, we point them all back. You notice previous is always behind. And so what will happen is current will go next, and then the previous will follow right behind it, which is what this thing does. Oh, wait, did we update previous too? Current equals next, prev equals cur equals temp. Sec. Let's run it, see if it works. Tell me more. Singing a little bit. Okay. Error found cycle in the list node. That means that there's infinite loop. So definitely not good. List node cur equals head.next. Temp equals cur.next. Cur.next equals the previous. So now we're pointing in front. The issue is that previous.next does not equal null. So at the very start, we need to turn the previous next one into null. Otherwise, it would point back at itself at the very start. So what happened was this node was previous, and it was pointing right here back and forth and back and forth. Boom. Please submit, please submit. We did it! Okay. So yeah, I guess I'll walk through it one more time real quick. First thing we want to do is we want to check if it's already reversed. That's the base case. We can just return there. Otherwise, we want to prepare to cycle through the list. So if we look a bit closely, test cases. We'll set the current node to the next node for the head. So now we want to start here because this is the first node that needs to be actually changed. This next value needs to be pointed at 1. But also, this 1 needs to lose its pointer. It can't point it anywhere. It's at the end of the list. Remember, once it's reversed, it'll be at the end. So the previous is going to become a head. And that next value, that field inside of its constructor that points to 2 usually, we're now going to point it to null. That way it points to nowhere. And now we have current. Now, as long as our current value isn't null, we can keep performing this operation forever because the only elements that we're accessing are actually before it. So if current isn't null, then what we can do is we can set the temp to the next one. So we'll store 3 temporarily. We're like, okay, we'll come there next. Then we'll set our current one. We'll point it backwards. And then we'll set the back, and then we'll point it backwards, and then now we're ready to move forward. So we'll set the previous one to where we currently are, and then we'll move current forward to the one that we saved from before. So now we just stepped forward while pointing this node backwards. We can do that recursively until the end. Another reason this is safe is because while current isn't null, every single thing in this would be fine as long as current isn't null. Because the only thing that can return an error is current.next. In the case that current is null, it won't have the next field. But because we account for that, these statements will always run, so you can have very clean, simple code like this. So I guess let me know if you guys like this video. I'm probably just gonna post it. I don't really like editing. I don't know. Let me know what works. Let me know, boys. Let's go.